This is the Module 12.3R video. So before we get started, you want to make sure that you have all the necessary files. So here on my computer, in my folder where I've been storing everything, just a couple things to note. I've got the Module 12.3 notes, I've got the code book, our data set, and then our Module 12 R code. So we're going to start out by looking at the notes. So in this note set, we're going to look at how to calculate different confidence intervals and how those confidence intervals can help us with different research questions that we might have about the BRFSS data set. So starting out, we're going to look at a confidence interval for a single mean. So our research question here could be, what is the mean BMI of people living in Kentucky during the year 2018? And so a confidence interval can help us estimate what that mean BMI is. So we're going to use R to see how to find that value. So let's minimize the notes here for a moment. And let's go ahead and open up the Module 12R notes in RStudio. All right, so we've got our Module 12 R code here. So just as a reminder, the first thing that we always need to do is to set our working directory. This lets R know what folder we're going to be working out of. And you can do this by clicking up here, getting the file path, and you'll see that my file path has already been set. So I'm going to run that code, and then I'm going to read in my data set. All right, and so my data now appears up here. So let's look at how we can calculate a confidence interval for a single mean. So remember that the variable we're going to be looking at is BMI, and specifically we're going to look at the BMI5 variable. So let's go to our code book and see if we can learn a little bit about that variable. Remember, if you hit Control F, we can search for different variable names, and here's our variable. So let's first look at how this variable is coded. So notice here if we have a value of 1 or greater, so this is a quantitative variable. And a couple notes here, they tell us how they calculated this based on other variables where people actually asked or answered questions. So this is a calculated variable. And then they let us know that this has 2 implied decimal places. That's going to be important later on. And then further, notice that if the value is blank, well, they have went ahead and grouped everyone that said don't know, refused, or missing, and they have already converted that to weights for us. And so they did this by if the weights or the heights, which were used to calculate BMI, if either of those were don't know, refused, or missing, BMI was automatically set to missing. All right, so going to our R code. So the first thing we're going to do is we're going to explore this variable a little bit. And the first thing I'm going to do is visually look at it by using a histogram. So we'll run this. Notice that our histogram here has a slight right skew, but it doesn't look too bad. And then also notice running this histogram, I'm not going to worry about changing the titles or the axes or anything like that. This is just to help me get a quick view of what this data distribution looks like. And the reason that's important is, if you'll remember, one of the things that we need in order for the central limit theorem to hold is that we need one of two things. We need either that the population distribution is normal, or we need the sample size to be large so the central limit theorem applies. Well, in this particular case, what we can do to see if the population distribution is normal is we could look at the data distribution. If the data distribution is normal, or looks, approximately normal, then we're probably safe to assume that the population distribution is, as long as we've taken a random sample. Now, in this particular case, it's got a slight right skew, but I'm not terribly concerned with this, but we could always check our sample size to make sure that we are safe. So the next line of code here is going to do just that. So parts of this code you've seen before. I'm going to highlight this piece right here. And if you'll recall, we've used that in the past to see how many missing variables we have. Well, for right now, I'm not interested in how many missing variables, or probably not missing variables, how many missing observations we have. I'm not interested in how many missing observations. I'm interested in how many observations I have. In other words, my sample size. I want to see if my sample size is large. So what I've done here is I've placed an exclamation point out front. R reads exclamation points as a not. So this is essentially asking R, can you tell me how many observations we're not missing? So running this line of code, we see there were 6,198. That is more than a large enough sample size for the central limit theorem to hold. Let's look at the mean of our sample. We can see the mean of this is 2,924.102. And if you go and look up reasonable values for BMI, you might say, well, that's not a reasonable value for BMI. BMI isn't measured on that scale. Don't forget that there are those 2 implied decimal places that we're going to have to take into account. All right, next we're going to calculate our confidence interval. And to do that, we're going to use the T.test function. So T.test. We're going to give the T.test function our data set and calling that BMI variable. We're going to include the NA.remove equals true. And the reason we're doing this is, remember, we've got some missing data in there, so we want to tell R, just ignore that missing data. And then finally, we've got this call right here, which can change our different confidence intervals, or probably confidence levels. So we're interested in a 95% confidence interval, so I'm going to change that to 0.95. So let's run this line of code. And here is our output, and you'll notice part of this output is the 95% confidence interval that we want. Now, if we wanted to learn a little bit more about that T.test function, we could do questionmark T.test. And R will tell us more about that. All right, so let's see how we can actually use this output to say something reasonable about BMI. So going back to the notes, you'll notice that I have copy and pasted that output in here, and I've highlighted the part pertaining to the 95% confidence interval. So a note on the data is from the code book. We know the values have 2 implied decimal places. So what this means when we look at our confidence interval, in terms of BMI, our confidence interval really goes from 29.07 to 29.40. So in conclusion, we can say we are 95% confident that the true mean BMI for the state of Kentucky was between 29.08 and 29.41 in the year 2018. Note that an individual is considered overweight if BMI is greater than 25. Since all of the values in the interval are greater than 25, this suggests that on average, Kentuckians were overweight in the year 2018. And so the part that I have here, the on average, is very important, and that's because we're learning about mean, or the population mean. So our conclusions need to be on terms of average BMI. All right. Next, we're going to look at how to calculate a confidence interval for a single proportion. So for this one, a research question we could be interested in is, what is the proportion of people living in Kentucky during the year 2018 who received a flu vaccine? So again, we're going to look at a 95% confidence interval. So let's go to our R code. Now the variable that we're interested in is the flu shot 6 variable. So let's go to our code book. All right, and we see here's the description for flu shot 6. Notice that flu shot 6 has 4 potential values. 1 is yes, 2 is no, 7 don't know, not sure, and 9 is refused in this case. So the first thing we're going to do is, just to get a handle on what this variable looks like for the state of Kentucky, is I'm going to run the table function. I see for the state of Kentucky, there was 2,612 yeses, 3,765 no's, and then just as a reminder, the 7 is don't know, not sure, so there were 7 don't know, not sure's, and there's no 9, so there was nobody that refused to answer. Now, if I'm going to calculate the 95% confidence interval, I have to decide what is the category I'm interested in, and then what's the complement of that category. So in this particular case, I'm interested in the proportion who are receiving their flu shot. So I'm going to consider everyone else that said no, don't know, and refused as the complement of that. So in order to calculate my confidence interval, I have to tell R 2 different things. I have to tell R my total sample size, and I have to tell R how many people were in the category I'm interested in. N is going to be my sample size. So notice this line of code is very similar to what we did before when we looked at a single mean. What we're doing here is we're finding the total number of observations where the data was not missing. The next line of code is similar, except instead of finding the number of observations that are not missing, I'm going to find the total number of observations who responded 1. Because again, 1 represents that a person said yes, they got their flu vaccine. So let's run both these lines of code. Notice that the values K and N now appear up top. Notice that K, which should be the total number of people that said yes, they got a flu vaccine, is 2,612, and this is the exact same value that we found when we used the table function. And then finally, to actually get our 95% confidence interval, we're going to use the prop.test function, and what we're going to give R is the number of people in the category we were interested in other words, the number of people that said yes, they got a flu vaccine, and our total sample size. So running this, we get some output that looks similar to what we saw before, and notice that part of this output is the 95% confidence interval, which is what we want. And again, if we wanted to learn more about the prop.test function, we could type in questionmark prop.test, enter. And we can learn more about that function. Going back to the notes, here we have that output copy and pasted and the interval portion highlighted. Now remember, as our data note, we want to define what our category is and then what the complement of it is. So in this case, we're considering the proportion of those responding no, don't know, or refused as the complement of yes. So in conclusion, we are 95% confident that the true proportion of people in the state of Kentucky receiving a flu vaccine in the year 2018 was between 39.65% and 42.1%. Since all of the values in the intervals are less than 50%, this suggests that less than half of Kentuckians received the flu vaccine in the year 2018. Next, we're going to look at how to calculate a confidence interval for a difference in means. So we might be interested in what is the difference in mean BMI for people living in Kentucky with good better health compared to the mean BMI for people living in Kentucky with fair or poor health during the year 2018. And again, we can use a confidence interval to help us look at this. So the first thing we're going to do is we're going to look at our two variables. Remember that our two variables now are going to be BMI, and then the variable that tells us about whether or not somebody said good, better health compared to fair or poor health is the RFHLT variable rather. So let's copy this and go to our code book. So here is our variable. So notice if a person says 1, they had good or better health, 2, fair or poor, and then a 9 was don't know, not sure, or refused. All right, so going back to R, first thing I'm going to do is I'm going to create two different objects. I'm going to call them good BMI and poor BMI. Good BMI is going to store all of the BMI information for those that responded they had good or better health, and poor BMI is going to be the BMI for everyone who said that they had fair to poor health. So to create these objects, first thing I'm going to do is call the BMI variable. Then from the BMI variable, I'm going to select all of those people or all the observations where the person responded 1 to the health variable. And then similar to construct the poor BMI object, I'm going to call the BMI variable from the data set, then I'm going to select all those people or observations who responded 2. So let's run this code. We see the good BMI and the poor BMI values now appear over here. So similar to when we worked with a single mean, I want to explore each of these two different sets of BMI sample data. So first, I'm going to look at the good BMI sample data. And I'm going to look at a histogram. And so here's my histogram. Notice it looks very similar when we looked at all of the BMI data. It has a slight right skew. And I'm going to denote the total number of people in this sample, and there's 1,613. So our sample distribution is slightly right skewed, so if I had concerns about whether or not the population was normal, I know that I would still be fine because the central limit theorem, this sample size meets that requirement. But we also have to check our second sample, which is going to be the, oh, sorry, I did these in reverse order. I did the poor first, so we'll go back up and do the good now. and we'll find similar results here. Our sample size is large enough for the central limit theorem, and we can look at our histogram. All right, so next I'm going to look at the mean and the standard deviation for each of my samples. We see there is a difference in the sample means, but remember we're interested in a difference of the population means, and then we have each of the standard deviations. Now, when calculating the confidence interval for a difference in means, you have to decide if the population variances are equal or not. A general rule to evaluate this is to use the sample standard deviations. If the largest sample standard deviation divided by the smallest is greater than 2, then you need to use the unequal variances method. So let's divide the larger sample standard deviation by the smallest. Notice we know that poor BMI standard deviation is the largest based off the output we just looked at. We see this value is less than 2, so it would be reasonable to run the procedure where we assume equal population standard deviations. For illustration, we're going to calculate it both ways. So here, notice we're going to use the t.test function again. This time I'm going to feed it both of these sample informations. And then I'm going to add in a comment that says var.equals true. var.equal equals true. And so this is saying it's safe to assume that the population variances are equal. On the other hand, if I didn't feel comfortable making that assumption, I could set the var.equal equal to false. So let's run both of these. So here is our confidence interval assuming equal population standard deviations. Here is the confidence interval not assuming equal population standard deviations. You'll notice the one not making the assumption of equal population standard deviations is slightly wider, and it always will be. The reason for this is it's accounting for a little bit of extra uncertainty there, and so it's created a little bit of a wider interval. It's going to be more conservative, and so if you have any questions about the population standard deviations not being equal to one another, and usually they're not, this is usually the safer bet. All right, going back to our output here, or our notes rather. Notice here is that output. So what does this actually tell us about BMI between the two different groups? Notice here in my data note, we have that information about the 2 implied decimal places, and I'm going to note that my analysis assumes equal standard deviations. You always want to document what type of analysis you did. So in conclusion, we are 95% confident that the true mean BMI for people living in Kentucky with good, better health is between 2.58 and 1.83 less than the mean BMI for people living in Kentucky with fair, poor health. Notice the reason that I have less here in the interpretation is because these values were negative. Note that since the interval does not contain 0, it is plausible that the two means are not equal to each other. In other words, that there is a difference in the BMI between those with good, better health compared to those with fair, poor health. And in particular, based off that sample data, it appears that those with good or better health have a lower BMI compared to those with fair, poor health. And then last, we're going to look at how to use R to calculate a confidence interval for a difference in proportions. So for this example, we might be interested in what is the difference in the proportion of people living in Kentucky with good, better health who received the flu vaccine compared to the proportion of people, that should just say the proportion of people living in Kentucky, living in Kentucky with fair, poor health who received the flu vaccine during the year 2018. All right, so again, going to the R code. So this time, notice we're still looking at 2 variables we've seen before. We've got that health variable, and now we've got the flu vaccine. And so what we're looking at, if we consider those with good or better health and look at the proportion of them who got the flu vaccine, does that differ from those who have poor health who received the flu vaccine? So the first thing we're going to do is similar to when we worked with means. We're going to create 2 different objects. One to store the information for those in the good health category and one for those in the poor. So what we've got here is I'm going to call good.flu. That's going to store all of the flu variable information for those that responded. They had that good, better health. So I've called my data set and the flu variable here. And then from that, I'm going to pull out all the people who said they had the good, better health. And then for poor.flu, again, I'm going to call the flu variable, and then I'm going to pull out all those people that said that they had the poor health. And so we'll run these. And we see the good flu and the poor flu now appear over here. And what we're going to do is we're going to look at tables for each of these. So let's look at the table of the people with the good, better health. And so here is their breakdown. We see that there was 1,876 of them that replied they got the flu shot. Where out of those with poor health, we see that 732 of them replied that they got the flu shot. And so now we can use this information to calculate the confidence interval, and we're going to do the same thing that we did with the single proportion, except we're going to do it for each of the two groups that we now have. So these first two lines of code, what they're going to do is they're going to find the total number of people that had the good health, and then they're going to find the total number of people of those with the good health who said, yes, I got my flu shot. So that's my N and my K. So we can run these two lines of code. And then we're going to do the exact same things for those with poor health. So again, this first line is going to find the total number of people in the poor health group, and then the K.poor is going to find the number of people in that poor group who did receive their flu shot. And then finally, to get our confidence interval, we're going to use that prop.test function again. Now, the two different calls that we need to give this function, before we just gave it K and N, well, now we need to give it both of the K's and both of the N's, and we do it this way. So to give it both of the K's, we say X is equal to, and then we've got C open close parentheses. That is a function, and what it's done is it's combining those two together. So it's combining the K and the good into one object. So R knows here's my two different K's. And then we do something similar for the two different sample sizes. So running this, you'll see that we get our confidence interval. And let's go back to our notes. So again, our data note, we want to make sure we know that the proportion of those responding no, don't know, or refused was used as the complement to yes. And then in our conclusion, we want to say we are 95% confident that the true proportion of people living in Kentucky with good, better health who received the flu vaccine is between 1 to 7% less than the proportion of people living in Kentucky with fair, poor health who received the flu vaccine during the year 2018. And notice the less than, again, it comes from the fact that both of these were negative. Notice, since the interval does not contain 0, it's not plausible that the two proportions are equal. So in other words, what this is telling us is those with good or better health are receiving the flu vaccine less than those who have poor health. And so this, there could be a variety of reasons for this, but we're able to conclude that based on these confidence intervals. So this concludes the Module 12.3 notes. As usual, if you have any questions ever about the code, or if when you work with your particular data set, something else arises that you want to look at, just let me know.